So welcome back, everybody. And this is actually our last session. Many of you are going to be busy with exams next week. And then I guess that you're going to travel after that to your final destinations for doing your master thesis. So what I was thinking of doing today is to point both to some of the material which we have. And since not everybody could attend this week due to many different circumstances, I've placed videos of lectures which I have done before on the topics on convolutional neural networks and also how to use neural networks to solve, for instance, differential equations. I also wanted to point to project number 2. So the deadlines are tentative, but if you now go to either the doc folder here and you scroll down to projects and you go into the folder 2022, you will then find the different files for project number 2. But we can also just dive into the link here. And if you scroll down here, you will find several of the topics which we have discussed through different lectures. And one is obviously about building your own code for neural networks using backpropagation, which we discussed before the winter break. And there are also slides on deep learning and on more advanced methods like convolutional neural networks. And finally, there is a set of lectures on convolutional and recurrent neural networks. And one of the topics which is also something you can look at is about the deep learning for solving differential equations. So one of the things which we haven't done and which we will not have time to do because many of you will be busy with exams this coming week and then you're leaving, is about decision trees and ensemble methods. So if you're interested in that, you could take a look at it if you want to. So the second project, if I'm now just going to go through the text here a little bit. So the second project is a little bit more open-ended. And I just put a tentative deadline to February the 15th. And for project number 2, as we've also been discussing, you can propose your own data sets which are related to your research. Or if you find other data sets, you can take a look at that. So one data set which many people looked at was the pulsar classification data set. This has been very popular. The thing which is nice there is that you also have scientific articles which describe the data. This applies also to many of the data sets which you will find at, let's say, Kaggle.com. The University of California at Irvine has a machine learning repository, which is very popular. There is from this repository, there's a credit card data set, which has been used by many people in order to test various algorithms, whether this is logistic regression, whether it's deep learning methods, decision trees, random forests, etc. And there's also a scientific article by Yen Lian. So if you want to venture into that type of data set, then what you should try to do is to see if you can beat their classification here. So this is a data set about the credit card debt, whether you are able to pay your credit card debt or not. And it has many, many different features like the age of the credit card owner, the education, employment status, etc., etc. I think that's something like 20 features or something like that. So you can use in the analysis the methods which we have discussed, but also if you have, if you are familiar with other methods which are not covered during the lectures, like support vector machines or random forest, feel free to explore these as well. I mean, in my lecture material, you will find discussions of these methods as well, but we have not had the time to discuss them properly. So there's also this, as I mentioned, this pulsar data. That this is an astronomy case, which has been very popular with many of you. There's also this article here by Bates et al., which can serve as a kind of reference for discussions. Then what comes here is obviously the possibility to also use other data sets. The basic structure of your project should be like project number 1. So you should start discussing the data, reading the data, and follow much of the discussions which you had in the previous projects. Then you need to include at least 2 central algorithms and explain the basics of the methods. Describe the algorithm and implementation and tests you have performed. And then you present your results and findings. And then you come with a critical assessment of all the data which you have been discussing. So like project number 1 as a scientific report. Then, if you're interested, and this is the kind of field which relates more to my own interest itself, you can use the deep learning methods to solve differential equations. And in this particular case, we've taken the diffusion equation in 1 spatial dimension and plus time. So it's normally called 1 + 1 dimensional problem. And the first step is actually to use traditional methods, and you can look up in my notes on computational physics or alternative sources how to solve differential equations by using, let's say, something which is called forward Euler or backward Euler methods. I mean, the kind of classical methods which are used, like finite difference methods, to solve differential equations. And then the next part is actually to solve the differential equations using neural networks. You can also, if you want to, you can look at an eigenvalue problem, but I'm just going to put this as an optional problem. So this allows you to explore the mathematical solution of differential equations with deep learning methods. And this is a field which is becoming very popular and very interesting, in particular for the solution of high dimensional equations, when you have many, many degrees of freedom. So one typical situation is relates to studies of turbulence when you solve Navier-Stokes equations, because when you want to study turbulence, you will often have to have a very fine grid where you describe your integration points. And when you make the grid very, very fine, that means that you're making the resolution very fine. And that clearly makes the dimensionality of your problem explode, because these methods are normally always translated in terms of matrices, which then represents the different spatial directions and time. And clearly, the larger the matrix is, the more intensive the calculation becomes. And that is a domain where deep learning methods actually have made quite some impact. And in, let's say, meteorology, weather forecasting, to be able to make predictions about possibilities for turbulence is something which is very, very important. So that's just one typical application. I also wanted to say a little bit more about the material which we have. So if you now scroll down a little bit and look at the different slides which we have. So since before the break, what we had was a discussion in this week of December the 12th to the 16th, where we actually went through the basics of neural networks. And we looked also at the backpropagation, and you will find videos about these methods. You will also find the lecture notes, etc. Now, in this week, since many of you could not attend, what I then took the liberty of doing is actually to reuse videos from a course which I teach at the University of Oslo, which deal with these topics. And you will have both the slides and the videos. So this course has actually more lectures than what we will have in total. But the hope is that if you watch these videos, and there are also links in the teaching material to other videos, which are very good. So I invite you to take a look at the lecture material, which you will find, obviously, if we now go back to the slides here. So if you typically dive into, let's say, let's take, for example, the discussions here on convolutional neural networks, what you will find then, obviously the links to the lectures here, but there are also some interesting videos here, actually quite good ones, on different on topics like convolutional neural networks. There's lecture series from MIT, which are pretty good. So there are also more resources. So you will typically find links like this, which I invite you to take a look at. And then when you just scroll down here, you will also find the my own lectures here. And the typical readings which I recommend is the textbook by Benjo and Goodfellow and Coville. And this textbook here has several chapters, and the chapters here can all be downloaded for free. It's actually a very good textbook. And that gives you many of the basic details behind convolutional neural networks and neural networks, and also many of the gritty-nitty details on how to tune a neural network. Any questions so far? Please feel free to break in. I just wanted to remind you of the teaching material which you have access to. And since not everybody could attend in this week, what I did then was simply to reuse videos which I have made in October last year. I hope that is okay. I mean, I didn't want to remake a video as long as I already have a pretty long video which I made on these topics. But what I wanted to say a little bit more about today is a topic which is also very interesting and can be very interesting for many of you. And this deals with recurrent neural networks. And then I wanted to use that also to make a kind of summary, a kind of overarching summary of what we have seen, and then point again back to project number 2 and also project number 1 if that is needed. And then we could use the end today to actually discuss the 2 different projects. So I'm going to switch back to the whiteboard if that is okay with you guys. So let me do that. So when it comes to the deep learning methods, which we have studied this semester, the central methods which we have looked at, so let's just quickly remind ourselves of that, the deep learning methods, and just a kind of pros and cons of their methods. So one is a standard feed-forward neural network, or what's also traditionally also called a multi-layer perceptual model. But I'm just going to write it in terms of the shorthand feed-forward neural network. So this is a feed-forward RNN. And this is normally what we call for a fully connected network. So it's fully connected. And with fully connected, what we mean then is actually that all the input nodes and all the nodes in the hidden layers. So if you think of this as the set of inputs which you give, we normally call these as input nodes or input neurons. And then we have sets of hidden layers. We can have as many as we want. We can make the network deeper and deeper. And then we have the final output layer here with a given number of nodes. It could be just one or many, depending on the kind of a problem you're dealing with. And this produces an output, which then is fed into a cost function. And in here, cost or loss function. And in here, we plug in the target and we compare the targets with the outputs from the network. And typically here, when we say fully connected, that means that every node from the input layer connects to all the nodes in the first hidden layer and so on. So this node would then connect with all the hidden nodes. And similarly, if we continue with this node, we would have all these nodes being fully connected. That gives us in terms of the unknown parameters, this would then give us a matrix which is very dense because the unknown parameters are given by the weights and the biases of the given hidden layers. So mathematically, this translates into a dense matrix. with all the unknown parameters. And these parameters are then trained by the backpropagation algorithm, dense matrix with weights. These are the parameters we want to train, plus what we call the biases, which are normally a kind of parameter which is set to be non-zero in case the weights happen to be equal to 0 by accident, because then the training would stop. So this is assumes that the data is well structured, and everything is then mathematically expressed in terms of matrix multiplications or matrix vector multiplications. So this is normally then mathematically described as what we call affine operations. So if you take a matrix times a vector, this would fall under the slot of the mathematically of affine operations. We assume here that the data is well structured and homogeneous. Neural networks are in, since you now are dealing with, if you think of an image, and if you have an image with, let's say, 200 times 200 pixels, this image with just one color then, one color channel. Normally you have 3 color channels, the so-called RGB channels. But suppose now you just have one color. That means that this image would then have 200 times 200, which is 40,000 pixels. And they define the input nodes. So clearly, if you then have 50 hidden layers, no, hidden nodes in the first hidden layer, you would then have 40,000 input nodes times 50 nodes in a hidden layer. That gives you the dimensionality of the first matrix. And then depending on how many hidden layers you have and how many nodes you have, you will get matrices of different dimensionalities. So this means that the dimensionality of the problem becomes quickly huge and then difficult to deal with. And if you then think of imaging, then convolutional neural networks, or just CNNs, they reduce this dimensionality by filtering. The easiest way to think of that, reduce dimensionality by filtering, and mathematically, this is the process of convolution, as it's described in the slides and also in the textbook, let's say by Goodfellow and Benjo and Coville. So by filtering is actually mathematically represented by the process of convolution. And then you can add to this, you can add when you reduce the dimensionality of your data set. And typically for an image, if you think of a picture of a house, the house has obviously windows and doors and corners and so on. So these will be features which you want to use to train when you set up your data. However, the house itself, I mean, may have the same color. And for those regions where you don't have of the picture, where you don't have a window or door or specific corner, then there is no need to use all this information. So if you have an image which has 40,000 pixels of a house, clearly the parts of the house which just contain the wall, which has the same color in the painting, this is some kind of information which can actually be filtered out. So when you're dealing with convolutional neural network, many of these networks, they are based on pre-trained images. So you can have images of animals, you can put animals into motion, or you can just have a set of images of houses or buildings, and then you can train a huge data set to be able to reproduce or predict whether this is a house or a bridge or whatever. So the filtering process is a way to, if you think of this in more overarching terms, it's a way to reduce the dimensionality of the problem. And it applies very well to images because many of the images have large areas which are actually not very interesting, like the painting of a house on the wall. You wouldn't keep all that information. I mean, it suffices just to have some few pixels there. So what does not work well with CNNs and also standard neural networks is actually the length. If the length of the data is unknown. So this is something which neural networks like CNNs and the feed-forward neural networks do not actually work very well with. So it does not work well with data of unknown length. I should also say that when you look at all these methods, like a convolution neural network, that can actually be stacked together with different filtering processes to reduce the dimensionality. And then you can have a standard feed-forward neural network, which you use for training. And then when you've been training, you can have another dimensionality reduction. And then you can have another standard dense feed-forward neural network, etc., etc. So you're actually free to play around with different structures. And in the lecture notes on building your own neural network code, there are several examples where you can use an application like Keras, which interfaces with TensorFlow, which allows you to set up the architecture of a given neural network in a very explicit and easy way, where you then can set up the number of nodes easily, the number of hidden layers, the kind of gradient optimization method you want to use, and the kind of activation functions you want to use, and what the output is going to look like. So whether you're doing a classification problem or a regression problem. Now, the final thing I wanted to say something about is about recurrent neural networks, and these are also very interesting. They fall mathematically under the same complexity box as standard feed-forward neural networks, because they deal with the full information and they normally do not include dimensionality reductions. However, inside a recurrent neural network, you can actually have CNNs. So you can stack things together, but normally a recurrent neural network is a field of deep learning, which allows you also to deal with data sets of unknown length. It works very well on sequences of data, such as time series. It has been very, very successful in natural language processing. So the standard RNN is a field of research which is very, very active. And it's normally also used on, and this can be used on data sets with unknown length. So what I wanted to do now is actually to just say something overarching about the structure of a recurrent neural network. And perhaps the easiest way to think of this is by studying time series. This is normally closer to the way we as physicists are trained to think about, but it has also been used in natural language recognition. And many, many other topics. But let's try to look at a simple example of a case which we as physicists typically will encounter. And now we are going to look at time series. And the way we can think of this is as a series of measurements which we make. And at every measurement, we could have some input and we could have some output at a given measurement. And then what we want then is to train our data in order to make predictions about what we may see at a later stage. So suppose you measure the velocity of an object at different time steps, and at every time step there is a force which acts on the system. And at every time step you would then measure position and velocity of this moving object, and then you would record this as a function of the force which is being applied. So let's consider the following case. So we have a differential equation, a very famous one. This is just Newton's equation for motion. We have the acceleration. Then we have some friction term, which is a velocity dependent term. So here we have the first term is the acceleration. The second one is a velocity dependent friction term. And then we may have something which depends if we have let's say a harmonic oscillator, we would also have the dependence on the position itself. And there could be an external force which acts on the system. So this is a famous equation, which I guess many of you have seen. You would start with some initial conditions. So this is how you start the system. So you would have some x0, which would be your x at the time t0. And then you would have a v0, which is your velocity at the time t0. And then typically what you would do now is to rewrite this differential equation in terms of two coupled first order differential equations, because we know that the velocity is just the derivative of position with respect to time. And then we would get an equation then which we could rewrite as m of dv of dt plus this parameter eta, which could represent some friction or air resistance or drag term, which depends on the velocity. And this is now given by the velocity plus x, and this is equal to the applied force here. And one of the standard ways by which we solve this type of equations is typically we would discretize the equations. And this is also the way we are going to collect the observations, because we will make observations at discrete times so that we will then know the position at a specific time. And we would discretize, and we could use, for instance, Euler's method. And I'm assuming that you guys are familiar with Euler's method, which is just a Taylor expansion of the position around a point t plus a delta t, a small time step. So using Euler's method, that gives us a very simple recipe. So what we would have then would be the update of the position. So this would be simply a time t of I, a discretized time, a given measurement at a specific time. And then we are doing these measurements with different time steps. So this would be given by the previous value, just based on a Taylor expansion around t of I plus delta t. And then we have plus a delta t, and then this is multiplied with the first derivative, which is just the velocity. So I'm putting an equality sign here, but in principle, this is an approximation, because we are taking away all the higher derivatives of the position. And then we have a similar equation for the velocity. So we would have two coupled differential equations, because we have the equation, if we now look at the equations we have here. So this is one of the equations. That would be the equation for position. And then we have the equation for the velocity here, because we rewrote the acceleration in terms of the first derivative of the velocity. And that means that this v of I, if we now look at the equation which we have here, this is the equation which we would now need to plug in when we are going to update the velocity here. So we would then have a v of I, the old value. There will be a plus a delta t here. And then what we would need then is to actually set in the acceleration and that specific equation here. So I'm just going to put a times, a question mark. So in order to see that one, we can just rewrite dv dt. That's going to be given by this parameter eta divided by the mass times the velocity minus 1 divided by mass. I'm just dividing out terms of x plus f, the force which you apply, divided by m here. So this is the quantity which we then would plug in here. So we can rewrite this one as a force, F tilde, which is now the original force divided by the mass. We have a parameter alpha, which is going to be this one. So this is going to be alpha v plus a parameter delta, which is going to be this parameter, multiplied with x. So I can rewrite everything now in terms of a v of I plus 1, which is equal to a v of I plus a delta t, and then I have an f of I discretized minus alpha v of I minus delta x of I. And you see now that I can actually rewrite this in a more compact way. So I can rewrite that in terms of the previous velocity plus a function f, which now depends on the previous velocity. It depends on the force which is being applied, and it depends on the previous position x of I. So this is a kind of repetitive operation, which now is going to depend. If we can now rewrite this, we could write it in an even more compact way. So we could think of this now as a function which sets up the new velocity, which now depends on the previous velocity, v of I minus 1. I have an f of I minus 1, an x of I minus 1, and then I have the new. So this is actually my old velocity, which you have here, this quantity here. And then it has the force at this position f of I. And then it has x of I here, not position, but actually time. So what we have now is a dynamical equation, which we now could rewrite in a diagram, in a graphical way. So if we now just focus on v and we skip x, and we write this in a diagrammatic way, the way we can think of this now is that we start with an initial velocity, v0. Then we continue and we reach a certain time here where we have this function f of I. There is an input force, f of I. It has also a position x of I. So this is being input to this function f of I. And this produces an output, which we may be measuring. So we feed this output. So this is the output from this one. So v of I plus 1. This is then fed into the next one, which will be our f of I plus 1. And so this quantity produces this new velocity, which we could actually put up here, v of I plus 1. Here we produce a new velocity, which could be an observation. So when I'm writing it like this, what I'm saying now is that I have some input, which is given by the force here. It takes the previous velocity, and now we make a prediction, which is this quantity. But this quantity is also used as an input to the next stage. But this would now be an observation, which we could have. So we could think of this as us making measurements at given time steps. And at every time step, we measure the velocity of an object. And we could then rewrite this till we have the final step. So this would just continue. We would have a new force input, an f of I plus 1. We have a new position, x of I plus 1. And this just continues and just goes on all the way till the final time. And in the final time, we just call this an f of tau here, which is our final time. There is a v final, which is our final measurement. And there is an input as well, a force f of tau. There is a position x of tau here, etc. So this is the way we could now think of this specific quantity. And the way we can rewrite this in terms of a kind of structure for a neural network is to think of the following. So we are now going to, if we are going to make a network, so the connection with a neural network is now as follows. So we could now try to generalize this scheme, this graphical scheme here, in the following way. So now we are having an initial input, the v0. So we know the initial velocity. Now this feeds in and now I'm going to simplify some of the notation here. It feeds in to the first measurement which we have. So now you could think of us making measurements. So we fix this F1 and X1. So these are external probes. So this is external input at a given time step. Now this produces a new velocity V1, which is fed in to the next operation, F2 here. And then we have a new input here. So this will be an F2 of X2. This feeds in an V2 to an F3. And then we have a new input, F3 and X3. And this continues all the way till the final time. So this is an F of tau. And then we have the F of tau, X of tau. And this produces a final output, V of tau. But now I'm going to rewrite the output here. So this is now what you could think of is that this F of 1 is something which is defined by a neural network. So what we have here is a target, T1. So this is the measurement. So we have a series of measurements now at every time step. So we have a target. I shouldn't write it like that. Let me just change the notation a little bit because this is not time. So I'm going to call the measurement which we make now as a V1 tilde. So that is our measurement. Now our network produces a V1. This is now fed into the cost function. I'm just going to draw it like this. So this is our cost function. So in here, this is fed in here, and this is fed in here. And then what we do then is that we perform the calculation with a specific cost function which we have. So this could be like the mean squared error. So suppose we want to now have a network which at every time step produces an output, which is then measured with the output which has been, or the target which has been measured. And then we could then train a neural network to produce a cost function, or like if it's a mean squared error, which is as small as possible. So we would then have a new cost function, C here. We have an output which comes from the network. This V2 is fed in here. And then we have a measurement, V2 tilde, which is fed in here. So these two quantities. And this continues all the way to the final time step. So we are now going to try to set up a neural network which is capable of performing this type of operations at every single time step. So we would have the same here. We produce a V3. There's a new cost function evaluation. We have a new measurement here, V3. This is the quantity we want to reproduce. That is fed into the cost function. Same with this quantity. And this continues all the way to the final time here. A V of tau, we have a new cost function C, and then we have the final time V of t. Now the final velocity at this time. So it means that at every step here, we train a neural network with the inputs from the previous steps. And then these inputs are now fed into a next step with this operation here. So that means that if you now look at what we have, we need to set up parameters which connect the external inputs with what is coming in here. This again produces an output. So you could think of this as the output layer in a neural network. So inside here, you would have a typical feed-forward neural network where you do the training. Alternatively, people can also use convolutional neural networks inside what you have here. So what we're going to do now is simply just to try to set up the parameters which need to be trained in order to retranslate what we had as a standard differential equation, where in this specific case, we know exactly what we need to evaluate. So we have the derivatives, which are given by this expression here. So we have a well-defined mathematical expression, and at every time step, we update the velocity, and then we arrive, after we have integrated up over all the time steps, we arrive at the final velocity here. Now, this could, in principle, be compared with a observation. So if somebody gives you the position or the velocities at given time steps, you could actually set up a procedure in your differential equation solver where you have observations and you want to compare your differential solver with the observations. But now what we're going to do is actually to replace these mathematical operations given by a standard differential equation solver procedure. We are going to replace that with a neural network. And that is the basic idea of a recurrent neural network. Now, the way we are going to set this up is a little bit, we're going to now replace some of the symbols with other symbols. So let's try to do that. So I just want to keep this at a kind of overarching level. So what you could think of now is that we now have some kind of hidden layer or some specific general function. So let's call this one H0. This is at the beginning. Now this feeds into an H1, and then we are going to open up this and just specify it in more detail of what this actually is. So we would have an H1 here, and then we have some input. So now I'm going to skip this F1 and X1, etc. So we are going to have now some X1, which is an input here. This produces an output, which we call Y1. And in here, we have a target, D1, which we are going to compare with the output from the network, C. So H now is going to stand for some hidden layers. And this continues now, and we move on to this H of 2 here. And we have an X2. This produces an output, Y2. And then we have a cost function where we evaluate this output with an input from the observation. So T is our target. And this would just continue all the way to the final point. And the way this is often written is now in a more compact way, in a graphical way. So we would now have the basic structure of a recurrent neural network. There is an output. So this Y now is just a vectorized input, output. There is a set of inputs. And then we have a box here, which now represents all the hidden layers. Now, the reason why I set it up like this is that if you think back to the measurement which we made here, what we would typically be interested in when we solve a differential equation could be the final velocity of the system. So that means that we would start with the initial conditions, and then we would end up with a final velocity here. And you could think of all the intermediate step as something which is perhaps less important. You could think of that as all these intermediate steps here as a kind of hidden set of steps which are then forgotten when we now have the final result here. And this is in a sense what we did here. What we are interested is actually the final output, which is this one. And all the other quantities which you see here are just intermediate calculation steps. But clearly what we could have is actually a series of measurements which are then used to gauge the quality of the output. I hope this connection with the differential equations makes it easier to see the kind of overarching motivation for a recurrent neural network. I think what we could do now is just to take, because we've been going on for close to an hour, so let's take a small break and then just stretch legs and have questions, and then we just meet in, let's say, 15 minutes, if that is okay. So welcome back. The aim of this lecture here is now to try to set up the type of structure which you will have in a recurrent neural network, and what kind of recurrent neural networks we may encounter. In the slides, the lecture notes, you will also find examples of programs which implement a recorded neural network using Keras as an API. But let's take a closer look now at the setup of a recorded neural network and what kind of training we are going to encounter. So let's try to rewrite what we did before the break in a slightly different way. So we are going to use this graphical presentation. So you could now think of some kind of input at a previous time. And let's just write this in a very generic way as some kind of dots here. And then I'm just going to put some dots again here. So that means that we have some hidden layers. And we get into a hidden layer. So we are going to rename these hidden layers in terms of different time steps. You can think of this as time. So there is a hidden layer, h t minus 1. And then we have an input here, which is an x of t minus 1. So this could be an external probe. It could be an external force which is applied to the system. And this hidden layer receives some inputs from the previous layer in the form of weights. So this is very much along the same lines as we've seen with a standard feed-forward neural network. Now, the input is also weighted by some weights, which we represent by a new matrix U. There will also be biases, which are included in together with the weights. And then this produces an output, which is then weighted with a new weight matrix, V. So you see the number of unknown degrees of freedom, they accumulate here, so they become larger and larger. This produces now an output, which we are just going to call Y of, sorry, let me just rewrite this one. So this produces an output Y of t minus 1. This is then sent in to the cost function at this specific stage, t minus 1. And this receives the target, which is our t, the target at t minus 1. And I'm going to put a tilde on here. So this is the observation which we make. You could think of now having made some observational experiments, and then you have a specific observation. Now, this feeds in to the next hidden layer where we do the training. So we have an h of t here, and there is obviously a weight matrix which connects the previous set of hidden nodes with the next one. And then we have a matrix U, which connects this external probe. We produce an output with this V here, and then we have a Y of t. This is fed into the cost function, where we then compare again some target data, a t tilde, a t here, and this continues all the way to the final time step. And I'm just going to put this in terms of these marks here of h, like this, and that feeds into the to the final output. So what we would have then is now the following. If you're now looking at the specific hidden layer here, or any of these hidden layers here, so we would then have an input to that hidden layer set of t, which is then given by some bias, b. So it's very much in the same way as we have for a feed-forward neural network. There is a weight matrix, which is then multiplied with the outputs from the previous hidden layer, t minus 1. And this receives an input from this external probe, multiplied with the value x of t. So this will be the input to the activation function. And then the output, which is produced by this layer t. So this hidden layer has now an activation function, which I just called for sigma. And this receives as input z of t. Then what I need, and now you see exactly what kind of training we need to perform. So we would need to have the gradients of these w's. We would need to have the gradients with respect to u's. We would need to have the gradients with respect to b. We need to take the derivatives of the activation functions as well in the same way as we built up a standard neural network. Then what we have is this output from this specific hidden layer. And this output is something which we are going to rewrite in terms of a specific function, G, which then takes this new matrix with unknown variables V. So this is a new weight matrix. It takes the output from the hidden layer, H of T, and then it has an additional parameter, C, which is a bias. So if we now go back to what we did here, so we get an input from the previous layer, H of T, which comes in here. That goes in here, and it's weighted by this matrix W with unknown parameters. And at every time step, we actually have to train these Ws. Now, in some applications, people keep this matrix U fixed, assuming that the type of external probe has the same behavior at each time step. So that can take away some of the weight or the heavy types of calculations which are needed for a specific feed-forward, a recurrent neural network. But let's now keep this as an unknown parameter at each step. So you see now that we feed in here, we need to have this W multiplied with the previous weights. We have this U multiplied with X, and then we produce N bias B. So if we now start marking these quantities, you can quickly see the unknown parameters which we need to establish. So this is now an unknown parameter. This is a new parameter. And then we have an activation function, which is part of the architecture. And then we get a new set of parameters, V, and we get a new parameter, C here. So compared with a standard feed-forward neural network, where we would set up the gradients for the weights and the biases, we have now two additional weight matrices, and we have an additional set of biases. So that means that the training becomes much more time-consuming by obvious reasons. So the whole idea now is that this is going to be compared at every time step here. We compare the output with the targets which we want to reproduce, and we do a minimization of the cost function at every single time step. And we will continue with that till we have the final time step. This kind of neural network is normally called a back propagation through time. So the way you would typically start training the network is to start at the last time step and propagate back in time. Now, each hidden layer here is something you can model. You can make it shallow. You could just have one hidden layer, or you could actually have a number of given hidden layers inside there, or you could even replace it with a convolutional neural network if you are doing some kind of imaging, for example, and you're looking at how what happens with images as a function of time. So this could be very relevant if you're looking at the response from a detector, where you would typically have the response as a function of time. So the this algorithm, which you have here, is now called the back propagation through time. So BBPT, BP, sorry. And this is called back propagation through time. This is the perhaps the most standard model. Now, there is one way you can reduce the computational complexity, and that is instead of you now feeding in the input from the hidden layer in the previous step, we could actually change this by just feeding in to the layer the output from the previous stage. So that would mimic much more the way we actually solve a differential equation. So we can simplify, as you quickly realize, I mean, this algorithm which we put up here is extremely time consuming. However, it's actually the algorithm which does the best job for us. We can simplify the computational complexity by looking at the following approach. And what could be done then? Suppose now that instead we look at the output from a hidden layer. So I'm just going to indicate this with these dots here, just to indicate that this is an output from a previous time step. This could now feed in to the hidden layer. So we have an age t minus 1. There is an input here, an xt minus 1. We have this matrix U. And then we produce an output by just using as an input here the output from the previous layer. So this produces an output y of t minus 1. This is fed into the cost function as c, and this now contains, receives as an input the target t tilde of t minus 1. But now instead of having to train weights, what we would do then is to just use this output with weights and feed that into the next stage, h of t. And then we have u again, and we have x of t here, and this produces a new output, y of t, which then is compared with the target which we have and the cost function, t of t. And this continues as input to the next hidden layer, and again and again and again. So we would also have a weight function here, w. There is a weight function, v here. But the training here is actually less computational intensive. However, we do lose some type of information. So this is one way to reduce the computational complexity. Now, one of the problems which we have with this recurrent neural networks is something which is called exploding gradients. So let's just look at that as the last piece in our discussions of recurrent neural networks. Now, there is also something which is called long short time memory approaches and so on. There are many, many different algorithms for dealing with these recurrent neural networks. But the basic algorithm, the one which is most used, is this back propagation through time. This is, as I said, time in computational intensive. However, it gives normally pretty good results. And you can use that algorithm. And if you look into some of the examples which we have in the lecture slides, you can actually use that to make predictions about what will come later. So you are not, constrained to train your neural network through all times, but you could just train it up to a specific time. And many physics experiments, they do exhibit some kind of periodicity. We know that if we have harmonic oscillations, this would typically be given by a sine cosine. We could rewrite everything in terms of Fourier transforms. And then in that specific case, the training could go as follows. We could train up to a given time and then use the model which we have trained to make a prediction at later time. This actually works extremely well when we have periodic functions or results which repeat themselves over time. So this is one of the, I'd say, one of the very interesting applications of this from a physicist point of view. Now, if we look at the problem with many of these networks, and in particular the recurrent neural networks, there is a problem with what we call exploding gradients. And one of the techniques which is then used to actually avoid that is simply to clip off the gradient. So there's a technique which is called gradient clipping. So let's just take a look at that, because this is a technique which, when you're writing your own code, which you could also apply to a standard feed-forward neural network. So the problem with RNNs, and you can easily see that, because what you're doing now is that you're repeating the calculation of these weights at every time step. And that means that the gradients at a given time step will depend on the gradients from the previous time steps. And since you're doing this many times, what you can risk is that the gradients may become very large. And that will obviously lead to training which doesn't function anymore. So the problem with RNS are often due to what we call exploding gradients. And I just wanted to show you how this can take place by a simple example here. So what we have is this h of t, and what I'm going to do now is to take away the bias. So, and I also take away the input from the external probe. So if we simplify it, this h of t depends on the weight matrix, which connects with h of t minus 1. Now, this operation is repeated many times. So this operation, since we are having measurements at many, many time steps, this operation is repeated t times for h of t, t times. So we would start at the time t0, and then we just keep repeating that. So what it means then is that we have performed something like this. So we have this matrix W, and let's now assume that this matrix is the same at each time step. So this is just a simplification which I'm making to illustrate the problem of exploding gradients. So we would now apply this matrix t times, and we start with an input h0. So if you now look at this weight matrix, we can obviously think of this as a matrix which could be diagonalized. So suppose now that we can find the eigen pairs of this matrix by performing a similarity transformation. So we have a matrix S, which is an orthogonal matrix or unitary matrix, but let's assume this is an orthogonal matrix. So that means that we are performing a transformation of the matrix so that it can be written out in terms of a diagonal matrix times this orthogonal transformations. And this matrix D, we know that when we perform this type of transformations, the eigenvectors are the same, but the eigenvalues are the same, and the eigenvectors change because we have this transformation matrix. So what we're actually looking at is an eigenvalue problem of this type here, times lambda. So this matrix now contains just the diagonal. So we have lambda 0, and this goes up to the dimensionality of that matrix, starting at 0 here. Now, so the eigenvalues of W are these lambdas, and we would have eigenvectors. So we have eigenvalues of W, eigenvalues lambda y, and then we have the eigenvectors and we simply label these eigenvectors with a little wi here, a lowercase letter. So that means that what I can do then is to rewrite my first hidden layer in terms of these eigenvectors. Now this forms, now we assume now that this matrix is a symmetric matrix. It's obviously a quadratic matrix, just to simplify all the arguments here. And then we can obviously rewrite that one in terms of this basis. So we are just using a basis which we assume to be an orthogonal basis, and we simply rewrite our H0 in terms of that one. It doesn't need to be an orthogonal basis. You can take any basis and just rewrite a new one in terms of that one. But let's assume that this is an orthogonal basis, and this is the eigenbasis of the matrix W. And we are assuming now that the weights are the same throughout the calculations. This is a simplification again, but it's useful in order to see how these equations actually can explode. So when we are training, we are now training the weights. And if I act on W of H0, this is going to give me H1, obviously. And this is now the same as a sum over all these alpha of i's. And clearly, when I act with W0 on Wi, no, sorry, W, this is the same as lambda of I times Wi. So this gives me lambda of I times Wi here. Now, if I now repeat this T times, what I end up with then is the following. So I have W acting on, sorry, not that. So I apply this to H0, T times, and that should give me H of T, which then obviously becomes equal to, since I'm applying this matrix again and again, I get an alpha of I of lambda of I of T multiplied with this eigenbasis. Now, you clearly see now that if we have ordered, suppose now that we have ordered this matrix in terms of a descending series of eigenvectors, eigenvalues, and then we end up with a lambda of D minus 1, then this will be dominated by the first eigenvalue. So assume now that lambda 0 is the largest one. So clearly when we perform this many, many times, this expansion will then be dominated by this specific eigenvalue, lambda 0 of T, multiplied with omega 0. And this contains also this alpha 0 here. So if this lambda 0 is larger or equal to 1, then we may get contributions to this H of T, which become very large. We may get contributions to this H of T, which can become very large. And this again leads, when we are now calculating the gradients, so that can give rise to what is normally called exploding gradients. As you can see, in order to understand this, we made a simplification, assuming that the matrices which contains the weights, it stays the same throughout all the calculations here. And to avoid this kind of exploding gradient, there is a standard trick which is called gradient clipping. So to avoid this, it is common to use a technique which is called gradient clipping. And machine learning contains lots of this kind of more ad hoc procedures. And you will be surprised to see how many such ad hoc procedures are normally involved in machine learning. So what you could do now, if we now define the gradient for the weights, so let's just call this gradient G, and then you would typically then put in an if test, so that if the norm 2 of the gradient is larger than a specific value, which you choose, I just write this a specific value here. What you would typically do then is simply to reduce the gradient by some parameter. So you could have some parameter epsilon here, and you divide that one by G, the norm here, and then multiply with a vector G. And then you have an NDIF here. So this epsilon is again a parameter, becomes a hyperparameter, which you need to tune. And then you divide by the gradient, the norm of the gradient, and then you have a new gradient. This is one way by which one tries to reduce this problem of exploding gradients. There are many other techniques, And if you go into this textbook by Benjo and Co-Will and Goodfellow, you will find many other techniques which are described in chapters 11 and 12, which deal essentially with practicalities, all these kind of small nitty-gritty details on how to deal with problems which arise in the computations. So running such calculations often leads to a lot of kind of hand tuning, which is simply needed because we may run into problems like this with exploding gradients. Now, this is going to conclude the kind of lecture part which we have in the course here. So I'm going to stop now sharing this one, and I'm going to go back to the basic setup for the course here and come back a little bit to the discussion of the project. So what you should have now, I'm also going to upload the video here a little bit later, so we will find that video. As I said before we started today, the videos which you find here are actually videos which, since not everybody could join, we had very few people coming both on the 12th and the 13th. What I did then was actually to use videos which I have made before. They cover a little bit more material than needed, but feel free to look into them. Now, if we go back to the project, which we have, so if we can either go to the doc folder here, and you will find the source files for the projects, or we can just go back to the display of all the lecture notes and the projects. So if you scroll down here, you will then find project number 2 here. So let's take a look at it again. And as I said, you should feel free now in project number 2 to choose your own data set, which is relevant for your research. We want you obviously to use the methods which we have studied. So you can use now neural networks, you can use convolutional neural networks, you can use recurrent neural networks. If you also want to use methods like support vector machines or decision trees and so on, which we haven't covered. So this is, after all, a 6-credit course. You can actually find this learning material if you go into my, let me just do that one. If you want to study recurrent neural network and so on, you can actually go back to my more in-depth lecture notes, and you will find notes about decision trees and ensemble methods. And if you're interested in support vector machines, there's also a series of lectures here, if you're interested. But I would more recommend that when you look at project number 2, that you try, if you're doing a classification problem, if that's a data set you want to study, I would just suggest that you compare neural networks or convolutional neural networks with logistic regression, which we discussed early in the semester. And then just leave these other methods by themselves. You can take the lecture notes where we describe the development and the setup of a code for a feed neural network, or if you're more familiar with TensorFlow, feel free to use TensorFlow or scikit-learn, which has a simpler neural network setup. And many of the same things which you did in project 1, the kind of scores which you set up, cross-validation, the bootstrap, which we discussed early in the semester, are things which you would typically include in a data analysis. And then clearly a critical assessment of all the methods and et cetera, is something which is important. There are also other data sets, like the Pulsar data set, which we encourage you to take a look at. This is a very popular data set. And in the last years, there were actually groups which dealt with this data. But I know that many of you also have your own data which you want to use. And for those of you who don't want to, let's say, dive into specific data sets, there is a part of the project which deals with solutions of partial differential equations. And in our case, we're just going to look at the heat equation. And if you're familiar with solutions of differential equations, you could compare that with the standard feed forward, or the forward Euler scheme. it's normally called the explicit scheme, where you have a pretty simple algorithm for solving the equations. And then you can compare that with the solutions using a neural network. And this part is then also discussed in the lectures, which you have access to. And you could take a look at it. There is also a good textbook, which is linked up in the lecture notes about that one. So that concludes essentially what I wanted to say this semester. And again, the deadlines for the projects are more made for your own planning. But since I know that many of you are starting to move pretty soon, it can be a good idea to just try to wrap it up as soon as possible. Okay, I'm going to stop here. I'm going to stop the recording.